I apologize. Somehow I clicked the wrong link, and even though it was set the right time, it was for a different meeting that was, I don't know why it was there, to be perfectly honest. But sorry, hopefully you guys can all see things now. Let me do one thing real quick. Attendance form, sorry about that. Let me back up just a minute so you guys can all see the things I just talked about. Yeah. Again, yeah, apologies. I don't know. Well, I do know what's going on, but I made a mistake. I'm sorry. So let me back up for just one sec so everybody else can get the things we just talked about. So real quick, for those of you who just got to join us, we're talking about how inverse functions and regular functions, or the functions they're inverses of, have interchanged domain and range. So a couple things from last time. If functions are inverses, then we know that f of g of x equals g of f of x is equal to x. And if functions are inverses, we know their graphs are going to reflect in the line y equals x. So here's an example we showed. We have this function 2 to the x plus 1, which looks like this, as a y horizontal asymptote at y equals 1. And then its inverse function, which is log base 2 of x minus 1, looks like this, as a vertical asymptote at x equal to 1. And these graphs, being graphs of inverse functions, are reflections of each other in the line y equals x. Now, the thing that we're going to take away from this, and that we're going to use specifically today, is the fact that when you find an inverse function, the x and the y things interchange. So specifically, the domain being all the possible x values and the range being all the possible y values means that the domain of a function is going to equal the range of the inverse function. And the range of a function is going to equal the domain of an inverse function. We can see that in this example. In this example, the domain of f, which is everything, is the same as the range of g, which is everything. And the range of f, which is everything from 1 to infinity exclusive of 1, is the same as the domain of g, which is the same. It's everything from 1 to infinity exclusive of 1. So the takeaway here is that we're going to be finding the range of a function instead of graphically, although we can still use graphical methods if they make sense to. We're going to find the range of functions by finding the domain of the inverse function. Hopefully that wasn't too quick for anybody. I did record a longer version of that, which I'll post later on, but yeah, sorry about that. Sorry again for, I should know that if no one's in the Zoom meeting, it's probably because they clicked the wrong thing. Sorry about that. I feel a little sheepish. Also, I drive to work on Road 102. There's a lot of sheep out there, some baby sheep. They're really adorable. I can't, they're really cute. That's all I have to say. On Road 102, close to Woodland. So if you drive like the north of Davis, like on the northeast corner of Davis, kind of up on north on Road 102 towards Woodland, you can see some sheep. And also some goats. There's lots of goats chewing things. Pretty great things you see from Davis and Woodland. All right, so let's talk about how we're actually going to find the domain of something and the range of something. Let's look at this example. We're going to find the domain and range of f of x equal to x plus 3 over 3x minus 5 without graphing. The domain shouldn't be too terrible here. For domain, we can look at this and see, okay, well, there's three things, right? Three possible things. We can't divide by 0. We can't take an even root, square root, 4th root, 6th root of negative numbers. And we can't take logarithms of negative numbers or 0. Just like in the previous example, right? We had a logarithm, the inside had to be greater than 0, which is why x had to be greater than 1. Here, the only possible domain issue is we need to exclude where the denominator is equal to 0. That's not too terrible. 3x equals 5, x equals 5/3. So we want everything except for 5/3. I like to draw a number line. It's not required. There's my 5/3 that I don't want. I do want everything on either side. So I want everything from minus infinity to 5/3 and 5/3 to infinity. I like to write the number line because it helps me remember that I need to write things from left to right. So I just look at this and I'm like, okay, the leftmost thing is negative infinity up to 5/3, union, and then from 5/3 to infinity. There's our domain. Let's talk about the range. So the range of this function is going to equal the domain of the inverse function. And I'm going to say a thing that's not always true, but it is true in this particular example. This function, x plus 3 over 3x minus 5, has a horizontal asymptote. Could you all tell me what the horizontal asymptote of x plus 3 over 3x minus 5 would be? It is a fraction. It's definitely 1/3. In this particular example, this function doesn't cross its horizontal asymptote, which is not always easy to know, which is why using a graphical method here probably isn't the best way to do it. But I'm going to tell you all, looking at this particular one, I can see, oh, y can't be 1/3. That's going to be the only value not in our range. We're going to see that when we find the domain of the inverse, but I just want to set you up to kind of see where we're going already. So let's find the inverse function. But I should back up just a little bit. That kind of idea doesn't always work. So I don't want you to take the lesson that you can always just find the horizontal asymptote. That's not going to be correct all the time. So in this case, it is. Generally, it's not true. So don't do that generally. Let's find the inverse function. So I'm going to set y equal to x plus 3 over 3x minus 5. And then we're going to switch. Now we're going to say x equals y plus 3 over 3y minus 5. All right, so now let's see what happens. We're going to solve for y. I'm going to multiply both sides by 3y minus 5. So I'm going to have 3y minus 5 times x equal to, you can skip this stuff or not. I'm going to write y plus 3 over 3y minus 5 times 3y minus 5. The whole reason we did that was to cancel the 3y minus 5s. Then we've got y plus 3 on the right, and we really need to distribute the x on the left. We really need to write that as 3xy minus 5x. You can write it as 3yx, but typically people write things in alphabetical order when you've got variables with different letter names. Okay. Here's the place where usually people tend, actually, this is where people tend to get stuck as well. But we want to isolate all the y's together. So we need to bring all the y's to one side so that we can then factor out the y. It doesn't matter what side, really. I'm going to pick the left. So I'm going to subtract y and get 3xy minus y. I'm going to add 5x to get 5x plus 3. And it should be super clear here. There's no way of simplifying this. You can't like add or subtract those together and get something more condensed. 3xy minus y is just 3xy minus y. The only thing we can do at this stage is factor out a y. And we're left with, you can also think of dividing out a y instead of factor, same words, just same meanings, different words. Y times 3x minus 1. Because if you redistribute that y, oh yeah, you're going to get 3x times y, and you're going to get minus 1 times y, which is exactly what we have. And then lastly, we're going to divide both sides by 3x minus 1. So we're going to y equal to 5x plus 3 divided by 3x minus 1. Or if you prefer, f inverse of x is 5x plus 3 over 3x minus 1. I know I'm boxing that like it's our final answer. It's not our final answer, right? We haven't done the thing yet that we've been asked to do, but it's still, it seems worthy of putting a marker around. So now we want to find the domain of this inverse function. To find the domain of f inverse of x, we're going to, well, again, we don't want the denominator to equal 0. So we're going to exclude where 3x minus 1 equals 0. Oh, that's going to exactly be where x is equal to 1/3. So that means our domain here is going to be, well, I can draw the number line again. There's my 1/3 that I don't want. I do want everything else. So my domain here is negative infinity to 1/3 parentheses union 1/3 to infinity. That domain is the range, I should say the domain of f inverse. That's my range of f of x. I don't feel like I need to write it again. I'm just going to put a box around it and say, yeah, that's my range of one second, Olivia. I want to say one thing and then. So I really want to make the point here. In this function, x can't be 1/3. But we switched x and y. So that really means that in this original function, y can't be 1/3, which is why 1/3 isn't in the range of the function. Question?
Is that a union?
That's a union symbol. Yeah, but yes, it looks like the letter U. Typographically, it looks slightly different, like you actually see it written in the book, but yes, it's the letter U essentially. And it just means we have this interval or this interval, right? You can have x for domain of f inverse, or I should say y for the range of x. Y can be any value in here or any value in here. It just can't be 1/3. Yeah.
For the domain, could you just write like x cannot equal 1/3?
You mean for the domain of f inverse?
Yeah, or for the range of f of x. I'm just wondering if it.
So that's a good question, but I don't have a great answer to. I suppose I'm in charge of the class, so I can say whatever I want. Really, like I'd be like, no, you can't do this. People get nitpicky about this kind of thing. Like, am I going to care a lot on the test? Probably not. I do encourage you to get used to using the interval notation though, because it is typically how people write things in future classes. So there's another way of writing this, which I haven't really talked about, which is both lazy and complicated at the same time. I know, right? Great combination. Another way of writing the domain here, if you really want, is it's the set containing x such that x is not equal to 5/3. That would be another valid way of writing it. It's called the set builder notation. The reason I don't like this is because once you start excluding a lot of values, it becomes kind of a pain in the butt, right? Not that this is really any better for that. So I will say, yes, I'll accept other ways of writing it other than interval notation, but I really, really want to stress, it is in your interest to understand how interval notation works. So that's my not very great answer to your very good question. Yeah, I would encourage you all to use set builder notation, interval notation, sorry. But if you're trying to write it on a test, you're like, damn, I don't remember how it goes. And you write x isn't equal to 5/3 as opposed to the domain is all of this, you'll be mostly right. You'll probably be 100% right. I won't be very, very strict about that. Okay, so find the domain and range of f of x equals the log base 3 of x plus 3. And I will point out we weren't told to not graph it. But let's just talk about doing it without graphing it. Domain. So for logarithmic things, we can't take the log of 0 or a negative number. Meaning, when I see a logarithm, I think, okay, the insides, the argument has to be greater than 0. That is the first thing I write down. Whatever is inside the logarithm has to be larger than 0. Can't be equal to 0, has to be greater than 0. And then we can solve for x. Something to be careful about. When you have fractions where you're excluding just one value, you essentially get the entire number line except for like that 1 point, or maybe a couple of points picked out here and there. But you're essentially getting the whole entire thing except for a tiny little bit. Whereas here, when you have a logarithm or a root, an even root, you're typically kind of cutting off half of the number line. So when I draw this, I want everything that's bigger than -3. So I want all of this over here. This is what we want, everything to the right of -3. So my domain is going to be -3 exclusive to positive infinity. We don't want any of this. There's our domain. There's not much more to it. The range, on the other hand, so here's the thing. You should kind of know the range of a logarithmic function just without doing anything. I still am going to show the work, but I want to point out, we know what the logarithmic function looks like. It looks like this, right? It's on our right hand. Mine not so good, but it kind of looks like that. Logarithmic functions have a range that is everything. They go down to negative infinity, they go up to positive infinity. They take a long time to go up to infinity, but like, okay. Here's how we find it, showing the work if we wanted to. So I'm going to find the range of this. So I've got my function y equal to log base 3 of x plus 3. And I'm going to interchange x and y. Or switch. So x equals log base 3 of y plus 3. So here I was trying to find the range, which means I was trying to find the possible y values. But now that I've switched x and y, now I'm trying to find the possible x values. Meaning I'm going to be finding the domain of this new inverse function. All right, let's solve for x. Sorry, let's solve for y. I'm going to rewrite this as 3 to the x equals y plus 3. And then if I subtract 3 from both sides, I get 3 to the x minus 3 is equal to y. Or preferably, f inverse of x is 3 to the x minus 3. Does this function have any domain issues? Do we see any of the 3 hallmarks that make us think there's a problem? No, there's no division by anything. There's no square roots or fourth roots or even roots. There's no logarithms. It doesn't have any domain issues. So there's no domain issues, meaning that the domain of f inverse of x, which is the range of f of x, is just everything, all real numbers. Now, again, you probably could have known that just by being like, I know what the graph of that looks like. It does the thing. It's going to be everything. I'm not missing any values. Questions about this one? I see some furrowed eyebrows, like there might be a question. Furrowed's kind of a great word. Okay, anyway. All right, we'll do a couple more examples. This is kind of it though for today. Like all we're really, I mean, yeah, inverses, yeah, but really the idea here is that you can find the range of a function by finding the domain of the inverse. That's the big takeaway from today's lesson. Although sometimes it's kind of terrible. Like this function here. Let's talk about domain and range. Let's see, what have I said to myself here? Yeah, sure. So if I'm ever asked to find domain and range of something, I'm always going to start with domain. You should always start with domain. It's just the more natural place to start. Also, it's alphabetical, right? X before Y. Start with the domain, which is the X things, before the range, which is the Y things. So I know that my insides have to be non-negative. Right? Unlike the logarithm where the insides had to be strictly greater than 0, here for the square root, the insides have to be greater than or equal to 0. Because you can take the square root of 0 and get 0, but you can't take a log of 0. It's undefined. There's a vertical positive there. All right, now I'm going to warn you all. It's very tempting to want to bring the x squared over there to that side. It's really the not safest way to do it. The better way, the best way to usually solve inequalities is to factor. You're going to factor this as 3 minus x times 3 plus x greater than or equal to 0. And then we're going to throw those zeros or those intercepts or whatever you want to call them on the number line. on my number line, I'm going to get x equal to 3 and x equal to -3. I suppose if I want to be very, very clear, the x equal to 3 came from this factor, the x equal to -3 came from that factor. It doesn't really matter, but I do want to make sure you guys know which one's which. And now we want to know when this expression is positive. It can only ever change signs when it goes through 0 or when it's undefined, but this is never undefined. So, okay, fine. Oh, this is kind of interesting. I hadn't even thought about that. Oh, no, yeah, sorry. That's not what I'm thinking. Okay, so if I pick something larger than 3, like 5, 3 minus 5 is negative, 3 plus 5 is positive, and negative times positive is negative. I will also point out you could plug in 5 here and see that 9 minus 25 is negative, and it doesn't work. But it's usually, this is kind of a simple example, but it's usually best to factor something so it's easy to tell if the whole product is positive or not. Then we can either see that all of these have odd powers. So the sign's going to change every time because each of those are representing crosses. Or you can keep plugging and chugging. If I pick a number like 0, 3 minus 0 is positive, 3 plus 0 is positive, and then positive times positive is positive. Pick a number like -4, 3 minus -4 is positive, 3 plus -4 is negative, and a positive is a negative. We want this thing to be positive, great. So we want this part here. We don't want the parts where it's negative, so we don't want any of this out here, but we do want the endpoints. Because it's totally fine to plug in 3, because 9 minus 3 squared is 0, and the square root of 0 is perfectly legit. So our domain here is -3 inclusive with a bracket to +3. Or if you wanted to write this using inequalities, you can write it as x less than or equal to 3, bigger than or equal to -3. Although I would encourage you all to do it like that. Let's verify that that makes sense. If I pick a number bigger than 3, like 4, oh yeah, that's not going to work out. Because 9 minus 4 squared is 9 minus 16, which is -7. And we can't take the square root of -7. In a similar way, oh, sorry, you can't see what I'm pointing at. In a similar way, -5 is not going to work. Because -5 squared is 25. And 9 minus 25 is -16. And we can't take the square root of -16 and get a real result. So this is our domain, because those are the only numbers that you can actually plug in here and get square roots of positive numbers, which are real. Range, on the other hand, so the problem with this example is that that function is not particularly easy to invert. Like, it's actually not invertible. Let's look at the graph of this for a second. So you guys might know the graph of this, although it might have been a while. If I was going to graph y equal to the square root of 9 minus x squared, well, we know what our domain is from -3 to 3. You could probably just kind of see it, but I want to show you a little bit more. If I square both sides and then add x squared to the left, can anyone tell me what the graph of this equation should be, or what kind of shape that? Yeah, you guys are on top of it. It's a circle. Now, here's the thing. Y equal to the square. Oh, well, first of all, a circle is not a function. It fails the vertical line test. But this y equal to the square root of 9 minus x squared is the top half of the circle, right? Because square roots only give you positive outputs. So it's a semicircle, and it's the top part. So this is the top half of a circle. And it looks like this. The domain is -3 to 3. And what's the highest value that this circle hits? Also 3, right? The y value, or the y-intercept, is 0, 3. So you could totally find the range just by saying, oh, well, I looked at the graph. The range is 0 to 3. If you don't love graphing, and maybe graphing is like, no, people often like graphing, not my favorite. Okay. Another way you could figure this one out without graphing it, but it would also without being able to find the inverse, because you can't really find the inverse here. So you can talk about the range just as, okay, what's the smallest y value we can get? Well, if my function is the square, and now I know we already know the answer, right? We've literally already written the range. But if you look at this for a second, you think about x being between x being between -3 and 3, what's the smallest this can be? Well, if I plug in x equal to either 3 or -3, what am I going to get for my function? Right. Smallest y value is 0. What's the biggest y value? Well, I want to make this as big as possible. When you have 9 minus a thing, the way to make that as large as possible is to make the thing you're subtracting as small as possible. So if x is 0, we get 9 minus 0, and the square root of 9 is 3. So the biggest y value is going to be y equal to 3. And we do get everything in between. So our range here. Now I know this is not very it's not really like an algorithm, right? It's not like a process where you do this and this and this. It's kind of just we talk it out kind of. And the thing about this is there are examples like this in the 17 series, especially when you've got this kind of expression and there's no real good way to talk about the range other than kind of just being like, okay, what's going to make this thing as small as possible? What's going to make this thing as big as possible? All right, that's probably the range. It's somewhat systematic, but it's not super exact, precise every time. It's kind of just what do I think is happening here? Okay.
I have a question about why for the number line on this problem, you included values, and on the other one, we just did.
It's an excellent question. So here on this number line, I care about the stuff being greater than or equal to 0. So I want to find out where on the number line my expression is positive and where on the number line my expression is negative. So I should point out, when I'm writing the minus and the plus and the minus here, I'm talking about what 9 minus x squared is doing. Right, so when x is bigger than 3, 9 minus x squared is negative. And when x is between -3 and 3, 9 minus x squared is positive. And when x is less than -3, 9 minus x squared is negative. And in this expression, since it's the square root of 9 minus x squared, I need that stuff to be positive or 0, right? Which is why we pick these points as well. Whereas in the previous one, sorry, I lost my spot here. Where did you go? Is that the one? No, where was the previous one? Sorry. Well, actually, we looked at this one previously, right? Which still has the same sort of thing, right? I didn't show as much work here, but I could have, right? Here I find the domain to be x plus 3 greater than 0. I know that -3 is where it's equal to 0. And so then I said, well, if I pick a number larger than -3, like -2, -2 plus 3 is 1, which is greater than 0. Check. -2 plus 3 is positive. Or I can just plug in -2 here instead of that. Over here, if I plug a number less than -3, like -4, -4 plus 3 is negative. And I want the stuff to be positive. But in this previous example, we don't care if it's positive or negative. We can totally divide by a positive number or divide by a negative number. That's okay. The only thing that the problem when you have a fraction like this or a rational expression like this is that we can't be dividing by 0. So in this situation, we only care about getting rid of the 5/3. But it's perfectly okay that if you plug in something here, the whole thing's positive or negative. Plug in here, right? It doesn't matter what the sign is because we're not worried about taking a square root of a negative or a logarithm of a negative. That's a really, really excellent question because a lot of times people do something like this and then check the signs and they're like, oh, I only want the positive part. No, you want where it's positive or negative if there isn't a square root or a logarithm. So we only worry about the signs of the insides if there's a square root or even root or a logarithm where you don't want to take a log of a negative or a square root of a negative. Yeah, good question. Thank you. Other questions? Okay, look at one more example. There's definitely a homework question like this next example. It's a little funky. And I'm going to talk about it in 2 different ways. Yeah. Domain and range. Start with the domain. So I've got 20 over x squared plus 4. Now, if I wasn't being super careful, well, there's a couple ways to make mistakes here. One way is to get the wrong answer by just saying, I'm going to set x squared plus 4 equal to 0, and I want to exclude that. I don't want the denominator to equal 0. Are there any solutions to that? No, right? If you keep going, you're going to get x squared equal to -4. And then when you see that, I hope you can see that we need this. We can stop right there, because when you square a number, it's always a non-negative result. So here, like, oh, there's no solution. Or you can go one step further and be like, all right, x is going to be plus or minus the square root of -4. So when you see a square root of a negative, oh yeah, that's not real. No solution, or I should really be, if I want to be very specific here, there's no real solution, which is all we care about is real solutions. And if we weren't being careful, we might at this point say that the domain is everything. But it's not. Because they very specifically told us in the beginning of this problem, find the domain and range of f of x equal to 20 over x squared plus 4, where x is greater than or equal to 0. They've told us the domain at the very get-go. So the domain here is just x being greater than or equal to 0, which is 0 inclusive to infinity. Now, the reason they've done that is to make it so that this function actually is invertible, which we may or may not do. We'll probably do. We got time. So let's talk about the range. I'm going to talk about the range in two different ways. I'm going to talk about what I feel like is the maybe easier way, but that also could just be because it feels easier to me with experience. I'm not gonna lie. Like I might feel this way because I've seen it a lot of times. But here's one way you could approach this: 20 over x squared plus 4. I might even try graphing it. Not very, very like precisely. But let's just think about plotting a couple of values. If x were to be 0, and I'm going back to a table. I'm going to pick a few values for x. If x is 0, y is going to be 20 over 0 plus 4. 20 over 4 is 5. If x is 1, y is going to be 20 over 1 plus 4, which is 20 over 5, which is 4. And if x is 2, y is going to be 20 over 4 plus 4, which is 20 over 8, which reduces to 10 over 4, which reduces to 5 over 2. So thinking about what the graph of this looks like, it's starting at 0, 5, and then I got 1, 4, and then 2, 5 halves. And it looks like it's maybe doing something like this, but it's never going to equal 0 because 20 over x squared plus 4 could never be 0. The numerator could never be 0. So thinking about this expression, it looks like the biggest that can be is 5. Why would that be true? Well, if I'm looking at 20 over x squared plus 4, what's a y? If I want to make a fraction big, I want to make the denominator big or small? Yeah, small. What's the smallest this denominator can be? Sorry, say that again. I think I heard someone say it. My listening is not always great. 4, exactly. The smallest this can be is 4 because x equal to 0 is the smallest you're going to make that denominator. 0 squared plus 4 is the smallest that can be. And to make it the fraction big, you make the denominator small. So the biggest y value is when x is equal to 0, and you're going to get y equal to 20 over 4, which is 5. The smallest y value. Okay, well, if I want to make the y values small, I'm going to make the x values large. How large can the x values get? Vary. Without end, right? They can get infinitely large. And if the denominator is infinitely large, the entire fraction is going to be, I don't want to say 0 because it's not actually going to equal 0, but it's going to be infinitesimally small. It's going to get closer and closer and closer to 0. So the smallest y value is approaching 0. So this says to me, oh, it looks like the range is going to be something like 0 exclusive to 5 inclusive. And that would be the range. So excellent question. So we kind of addressed this already, but I think it's worth looking at again. Someone asked, why for some of the questions to find the domain, you said it equal to 0, and others you said it to be greater than or equal to 0. And it's exactly the thing what's your name again? Katie. I was like, I think it's Katie, but not quite. I should know that's my wife's name is Katie also. So to answer that question, I think it's worth seeing again. We set it to be equal to 0, really when we're excluding 0. So in this example here, we set 3x minus 5 equal to 0 because we don't want to divide by 0. But in these other two examples, here, we set the insides to be greater than 0 because we don't want to take the log of 0, but we also can't take the log of a negative number. And the same sort of idea is true here. For the square root of 9 minus x squared, we set 9 minus x squared to be greater than or equal to 0 because we can't take the square root of a negative number. So that's why we're sometimes setting it to be greater than 0 or greater than or equal to 0, and sometimes just saying we want to exclude where it's equal to 0 because we don't want to divide by 0. You really, some people, I should also say, sorry. Some people do this by saying we want 3x minus 5 to not equal 0. That's another way you can write that. It's just never what I've liked to do because usually you're trying to solve the equation. Like, okay, we don't want